Hello, everyone. Welcome to CP 517-WS Digital and Computer System Architecture. I'm Professor Hang Liu. This is lecture 4, part 2 of pipelining the 5-stage execution workflow. Okay, so the left side showed us the 5-stage workflow of the instruction. You have instruction fetch, instruction decoding, execution, memory access, and write back. So if we don't have the pipeline, it would be very weird that we always put the data from instruction fetch to IF/ID register. And then when it goes to the end of instruction decoding, we also write the data in an intermediate register, right? If you remember, we have this IF, ID, EX, mem, WB. So if we don't have pipeline, so every time we only have one instruction occupying the entire 5 stages, okay? There's no need for us to use this kind of IF/ID. Similarly, ID/EX, etc. The reason is because when you are passing the value from the first component to the second one, the other components are idling, waiting for it to be used, because this is entire 5 stages are exclusively owned by one instruction, right? Well, if we do pipelining, what is pipelining here? This is the pipelining. So you have one instruction at this IF register, ALU memory access register, write back. Second instruction is like this, right? So assuming we have 4 instructions, so every cycle we submit one instruction. Like cycle 4, we're submitting this instruction. Cycle 2, all right, sorry. Cycle 1, we submitted this instruction. Cycle 2, we submit this one. Cycle 3, we submit this one. Cycle 4, we submit this instruction. So that means at the specific cycle, for example, in cycle 5 or cycle 4, at cycle 4, the first instruction, this instruction, is doing memory access, and this instruction is doing AI. I'm sorry, excuse me. So instruction, cycle 1 will launch this instruction, right? And cycle 2 will launch this instruction. Cycle 3 will launch this instruction. Cycle 4 we execute this instruction. So you can see at cycle 4, the first instruction is at memory access, and the second instruction is at execution. The third instruction is at instruction decoding, and the fourth instruction is in instruction fetch. So you can see, assuming you have this 5-stage components like instruction fetch, instruction decoding, execution, memory access, and write back. So you see, at the specific cycle of cycle 4, different instructions are actually using different components of this 5-stage pipeline, right? So at this moment, if you go back here, see, you might say here, like, this is the instruction 4, right? Instruction 4 is using this. Instruction 3 is using instruction decoding, and instruction 2 is using execution. Instruction 1 is doing memory access. So you can see different instructions have their own context, and they are using different components of this 5-stage pipeline, right? In this context, you need to have the intermediate register, because otherwise, once instruction 4 is finished, it's gonna potentially pollute instruction 3 if you don't have this buffer in between. Okay, this is very important. That's the reason we have this like a cross stage registers like IDF/ID, ID/execute, etc., right? And then whenever you have anything, it does not pass across the stage. Like whatever you have here, it stays here. Whatever you, the first one, and the second one stays in the second one. So this always goes to the intermediate register unless it's like right back, right? Okay. So once we have this pipeline, you can see every cycle we launch one instruction. At the end, right? At the end, you see every cycle you have one instruction finished, right? So then what's the throughput of the execution? Clearly, every cycle you have one instruction finished. So that means it is one cycle per instruction. So the throughput is like, or a cycle per instruction. It gives you an illusion. It's like one clock cycle per instruction, but actually every instruction takes 5 cycles. This is the power of pipeline. Even one instruction takes 5 cycles because at every cycle, different instructions are using different components of the 5-stage pipeline. Then you can see actually every cycle, it executes 5 instructions, this 5-stage pipeline, right? Okay, this is very important. The key idea of pipelining is to improve the resource utilization. So you have these 5 stages, 5 function units, and then every cycle, different instructions are using different function units. So then this 5-stage pipeline function units are fully saturated, and then you get the best performance. In this case, it's 1 clock cycle per instruction, right? Okay, so why don't you guys use 15 minutes to understand how the pipelining gives you better performance? Consider the uni-pipeline processor. Assume that it has 0.5 nanosecond clock cycle, uses 4 cycles for ALU and branches, 5 cycles for memory access. Assuming the relative frequency of these operations are 40%, 20%, and 40% respectively. Suppose that due to clock skew and setup, pipelining the processor adds 0.1 nanosecond of overhead to clock, ignoring any latency impact. How much speed up the instruction execution rate will you gain from a pipeline? Okay, can you use 15 minutes? Pause this video here, using 15 minutes to solve this problem. Okay. Okay, here we go. This is the solution. Without pipeline, you can see the time is CPI multiplied clock cycle. It is 0.4 plus 0.2 because both of them are 4 cycles. So it's multiplied 4. And then for the another 40%, it's the memory operation. So it's 5 cycles. And the water cycle time is 0.5 nanoseconds. So total is 2.2 nanosecond per instruction. With pipeline, because your CPI is 1 and the clock rate is increased by 0.1 nanosecond. So it's 0.6 nanosecond. So we can see the speed up of using pipelining over without pipelining is like 3.7 times. So by doing this, it's you purely gain, you change nothing, okay? You just do the pipelining scheduling, you get a 3.7 times faster. That's a lot of saving, okay?